Okay, good morning. Was it good to have a break? I felt that way. Okay, today we are on lecture 15. So I was looking at the plan for all the lectures in this course, and I'm going to make a change. So early on in the beginning of the semester, I posted this planned lecture contents for fall 2015. That is wrong. That should be 2017. Anyway, so I posted this, right? This is what I've been using for some years. And every year, what happens is towards the end of the course is when I do inverse airfoil design. Right, so this part. We do airfoil design in this course towards, and that usually comes towards the end using this Profoil design code and the M-foil interface. We have a project 1 for symmetric airfoils, and then we have a project 2 for cambered airfoils. And it kind of gets crowded towards the end. Those projects are sort of crammed in at the end of the semester. It goes by too fast, and it's always been a little unsatisfying. So I was thinking about that, and I thought there is no reason why I shouldn't move that upstream and swap some of these things to a later point in the course. So here's what I'm going to do. This part, and the lectures are slightly off. I'm for some reason I'm about one lecture behind the plan. I don't know how that happened. Maybe I'm talking too much. Yeah, so this part is basically elementary flows, thin airfoil theory, all the way till here. Right, this part is essentially, let's call it thin airfoil theory. And I used to call it chapter 3, and I think I'm still going to call it chapter 3, except I'm going to do it later on. So I'm going to move that to somewhere here. And so what that will help us do is talk about the Profoil code in inverse airfoil design, and then actually get started on the projects sooner. So one of the other things that will happen is, I think I gave 2 weeks for homework 3. So homework 2 is going to be due this coming weekend, right? And then there's 2 weeks for homework 3. I'm going to reduce the scope of homework 3 and make it shorter, maybe a week or maybe a week and a half. I haven't thought through it. So there is one problem in homework 3 that helps with project 1. So I'd like you to do that, but I'd like you to kind of focus on that, and I'm going to remove the rest of the problems from homework 3, and maybe I'll give it at the end of the course as a new homework. So homework 3 will be reduced in scope, and the time for homework 3 will be reduced. The focus will be on preparing you for project 1 so that we can get started on project 1 soon, and you'll have time for project 1, project 2 earlier in the semester rather than cramming it towards the end. So I think that will work. I don't see any reason why it shouldn't, because I think these topics are somewhat independent. So there is no reason why I shouldn't move this towards the end. And as you're working on the projects, we can work on thin airfoil theory in class. Okay. Any questions? Yes?
Question or 2 questions on homework 2. One is the type. I noticed in your samples you used to specify the type 2. And the other is Mach number, if that matters, or way you would adopt.
So type 2 and Mach number. Okay, and then what is the other? Those are the two questions?
Yeah.
Okay. Well, we'll be talking about type 2 now. Do you have a specific question on Mach number?
If it's not specified, should we just go with 0 or?
Yes.
Okay.
So type 2 will be discussed now. Mach number in homework problems, if not specified, put it as 0. And this is default. If you don't say anything about Mach number, it will automatically be 0. And this means it is incompressible flow. And the results from incompressible analysis are probably going to be valid up to Mach number of 0.2, because the flows are essentially incompressible up to about 0.2, 0.2, 0.3, something like that. Okay. So I have a couple of topics to finish on X-foil. One is this type 2, and the other is just a very quick demo on how to set flaps. So we'll talk about those things, and then we'll move to inverse airfoil design today. Any questions? Okay, so let's get going on that. So we know about Reynolds number. We have talked about Reynolds number before, but just to recap, Reynolds number denoted by RE is rho v L over mu, where L is a length scale, usually the airfoil cord for airfoil analysis. Rho is fluid density. V is free stream speed. And mu is coefficient of dynamic viscosity. And this is pronounced mu. There is another coefficient of viscosity, and that is called nu. So whenever we talk about atmosphere, air properties, there is this other coefficient which is called coefficient of kinematic viscosity. And this is nu, nu. So nu is simply mu over rho. And so all of these change with altitude. So if you go up in altitude from sea level, mu will change, rho will change, and nu will change. So you can look up atmospheric properties from a table, standard atmosphere table, or from some kind of online calculators, or you can write your own program. But those data sources will have a listing of rho and mu, or rho and nu, and from that you can calculate Reynolds number at any altitude given a velocity and the chord of the airfoil. Now, so nu, just for reference, is 1.46 times 10 to the power minus 5 in SI units for standard sea level air. So Reynolds number can also be written as V times L over nu instead of rho V L over mu. So there are two ways to write Reynolds number. One is with rho and mu, or second way is with nu but without rho. Okay, so one of the problems is that when you calculate Reynolds number for an aircraft in flight, and let's just assume steady level flight for convenience, when the airplane goes faster, like take this for example, if the airplane flies faster, Reynolds number increases. So you can't say this airplane, for this airplane the airfoil operates at a Reynolds number of 3 million. That 3 million will work only for one speed. If the airplane is faster or slower, the Reynolds number will change. So we talked about in Xfoil how you can do analysis at a given Reynolds number. So that means if you calculate the drag polar, that drag polar is valid only for one lift coefficient, right? One velocity. So how do you deal with this? Because at different velocities you need different Reynolds numbers, and that means you have to calculate the drag polar over and over again. Okay, so velocity changes with CL. Right? So when you change lift coefficient, velocity changes. So there's no point in calculating drag coefficient at one Reynolds number, because that will be correct only for one velocity. So velocity changes with CL, and so does Reynolds number. So that means we need some way by which we can account for this. So the way to do this is to look at how velocity changes in flight for an airplane. So for an aircraft in rectilinear flight. Rectilinear flight is cruise. This will definitely work for cruise, but it will also work for normal climbs or descent. So when an aircraft is in rectilinear flight, lift is almost equal to weight for the most part. So this is true So if we write lift is equal to weight and write that as half rho V infinity squared S CL, then we can write lift coefficient is 2W over So now this is the equation for lift coefficient, and Reynolds number is V infinity C over nu, this nu from the previous page, and C is the chord. So we can now plug these things in or connect these two equations, and we will get, I'm going to skip some steps, you can fill it in, and we will get Reynolds number is Vc over nu, V infinity C over nu, and substitute for V infinity with lift coefficient, and you will get C over nu times square root of 2W over rho S times 1 over square root of CL. And now you can now write the expression Re times square root of CL is C over nu and for a given aircraft flying at a constant weight, this is a constant. So everybody remember what C and S are? C is the chord. What is S? Planform area, right? Not span. Somebody said span. So S is the planform area, wing area. So wing area and constant chord are constant for a given geometry. If you're flying at a certain altitude, atmospheric density is constant. And as long as you're looking at it at the airplane performance at a given weight, this is a constant. So that means as lift coefficient changes, velocity changes and Reynolds number changes. But Reynolds number times square root of CL is a constant. So when you're analyzing an airfoil for a particular aircraft in rectilinear flight, you don't run X-foil at a constant Reynolds number. You tell X-foil as lift coefficient changes, change Reynolds number so that Re times square root of CL is a constant. So the assumption here is that lift coefficient of the airplane is fairly close to lift coefficient of the wing, which is true for most normal airplanes, where the wing is the big lifting surface and the tail is a small lifting surface. So most of the lift of the airplane comes from the wing. And what you can further go and say is that this is approximately the lift coefficient of the airfoils. This is also usually true. So you can say Re times square root of CL, which is CL of the airfoil, is approximately C over nu times 2W over rho S. And this is equal to constant. So codes like Xfoil, quite a few airfoil codes, but especially codes like Xfoil, which are used by so many people for practical day-to-day airfoil design, aircraft design. So they've thought through all these things, and these are features available in the code. So rather than running Xfoil for many Reynolds numbers, one for each speed, you can actually go and say run it at a constant Re times square root of CL. And that's what is the type 2. So in Xfoil, in the upper menu, so if you use type 2, Xfoil will do analysis at a constant Re times square root of CL and Mach times square root of CL. And type 1 analysis, type 1, which is the default, right? Normally when you don't do anything, it assumes type 1. So type 1 analysis will assume that Reynolds number and Mach number are constant throughout the drag polar. So when you're comparing with wind tunnel tests, for example, wind tunnel tests will have data for some Reynolds number, say 3 million, and it will be the same, 3 million will be the same Reynolds number for the entire polar. So when you're comparing with wind tunnel results, it makes sense to use type 1, but when you're doing it for an actual aircraft analysis, it makes sense to use type 2. So the way it works is, in type 2, if you input, if you say Re 3 times 10 to the power 6, this means that you're telling Xfoil Re times square root of CL is 3.3 times 10 to the power 6, 3 million. And if you input M equals 0.2 or M.2 in the command line in the list of keywords, this thing seems to be going out of focus. Okay, so if you input Mach M.2, that means M times square root of CL is 0.2. So we talked about how to calculate RE times square root of CL for an aircraft. So if you know the aircraft parameters, you can calculate RE times square root of CL. Like that, you can calculate Mach times square root of CL. Again, Mach number also changes with velocity, right? So Mach number is velocity over speed of sound. So when the aircraft velocity changes, Mach number changes. And aircraft velocity is going to change with lift coefficient. And so if you do Mach times square root of CL is 1 over A times 2W over rho S, where W, and when you're calculating, when you're doing everything in SI units, you remember to use newtons, not kilograms, for aircraft weight. So this is actual weight, this is not mass. Even though a lot of data sources will say aircraft weight is so many kilograms, right? That's because in common day-to-day usage, people talk about weight in kilograms, and that's true in aviation too. Kilograms or pounds or something like that. So if you're going to work in SI, remember to convert the kilograms, that's mass, to weight. So S is wing area, A is speed of sound. This will vary with altitude. Rho is density. That will also vary with altitude. Nu is coefficient of kinematic viscosity. This will also vary with altitude. So you have to get these from atmospheric tables. So I'm not deriving this. I mean, it's a pretty simple thing. You folks can do that. Okay, so the good thing about this is now if you run your Polar, the calculated polars will automatically when you run Xfoil with type 2. So, but the important thing is the way you calculate polar is you use PACC, right? Polar accumulate. You have to put type 2 before you do polar accumulate. So this is the way codes work, right? This is not, I mean, the way apps work these days are different. Like if you take Google Maps or something, and you do something and you change settings, it'll update the map, right? That's not the way most scientific codes work. So if you do a full analysis and then you type 2, it's not going to go back and change all that stuff because the calculations are done based on the settings you give before you start the calculations. So use type 2 before giving PACC or some command like that. So just for as an example, let's assume RE times square root of CL is 3 million and M times square root of CL is 0.3. That means at a CL of 1, Reynolds number is what and Mach number is what? Come on, it's easy. Yeah, it's a set value, right? At a CL of 1, Reynolds number, actual Reynolds number is 3 million and Mach number is 0.3. But only at CL of 1 will this Reynolds number be 3 million and Mach number 0.3. At a different CL, like say CL of 0.5, let's say 0.25, what will the Reynolds number be? 6 million, correct. And Mach number? 0.6, right? And at CL of 0.05, this is a very small lift coefficient. What is Reynolds number? Anybody have a calculator handy? $13.4 million, yes. And Mach number? This is typical of some kind of a general aviation airplane. What's going on? We are making it go supersonic. Mach of 1.34. So that means if we make X-foil do an analysis at this Reynolds number of RE times square root of CL of 3 million and M times square root of CL of 0.3, the polar plot, which will look like this, right? This is drag polar, CD versus CL. And that'll be something like this. So at a CL of 1, this corresponds to RE equals 3 million and Mach number 0.3. At anything lower than this, CL, as the CL reduces, velocity of the airplane is increasing, right? In level flight, an airplane going fast is flying at a small CL, and therefore Reynolds number increases. So as you go this way, RE and M increase. But because we have kept RE times square root of CL is constant, that's automatically taken into account in X-foil. And as you go this way, RE and M decrease. So this is all built into that Newton iteration that we talked about. You know, X-foil has that viscous inviscid interaction, so it's iterating, right? While it's iterating, as the lift coefficient changes, it will automatically change Reynolds number, which is, think about it, it's such a convenient thing. If you're designing airfoils for aircraft, without this it would be a real pain because you would have to, you can generate a polar, but that polar is valid only at one place, one point. Then you have to generate another polar for another point, and then you have to actually look at a family of polars for every now this is automatically takes all that into account. So what's the deal with this? CL of 0.05, Reynolds number is 13 million and Mach number is 1.34. Somebody? I mean, you can think through that. What's going on at CL of 0.05? Very small CL, yeah. Good. I think you're. Yeah, negative angle of attack is not necessarily bad. You can have an airplane at a slightly negative angle of attack. If you have a highly cambered airfoil, you can fly at a slightly negative angle of attack in very fast cruise. That's okay, like -1 or something. That is not too bad, but CL of 0.05 is almost like a dive. It's so fast that it's probably not in level flight. So if an airplane is in a dive, it will be in a very low CL or even CL of 0. So that RE times square root of CL expression is no longer correct, right? So you can make an airplane, like a lot of World War II airplanes experienced shock waves because when they went into a dive, the velocity became so high that over the wing the flow accelerated to sonic speeds, right? Here we are even making the free stream speed 1.34. So way before this happens, the airplane will have other problems, right? It might exceed the structural speed and the wings might twist off and all kinds of things will happen. But X-foil doesn't know all that, right? If you just say go calculate, it's going to go calculate. The problem though is X-foil is not meant to handle shocks, and so it'll kick out, it'll probably give some error messages. So somewhere here at some low CL, X-foil will start spitting out error or warning messages. Something like you won't know what it is unless somebody kind of tells you or you realize. So it will say CP calc Mach number too high. So usually you won't know what does that mean, CP calc. CP calc is some subroutine in X-foil, and in that they've put error messages saying if the Mach number is too high, put this warning. So when you do a polar accumulate, right, when you do a PACC, you won't know beforehand when these things are going to happen, and X-foil probably won't even converge. So that's actually a good thing. So you can blindly give a polar analysis saying go from here all the way up here and then go from here all the way down here. But at some point when this problem happens, X-foil won't converge, and so it won't write the data to the file. So that's a good thing. But this is what can happen when you go to very low CLs. You're violating these approximations of level flight or rectilinear flight approximation. The airplane is in a dive. It's usually way beyond what we are interested in. The other good thing is if you do a type 2 analysis in the polar plot itself, on top it will say RE times square root of CL is 3 million. So that's why I keep insisting that I want to see polar plots from pplot rather than from you taking all the data and putting it in MATLAB and plotting it. Not that anything is wrong with plotting it in MATLAB, it's just that you will probably not think of putting all those things, and so I won't know at what conditions you ran it. Whereas if you give me a polar plot from pplot, all those things will be up there and I know. Or if you're collaborating with other people on an airplane design and you send them a pplot thing, they will know what the conditions are, including that you ran it at type 2 and such things. All right, so now let's talk about how to simulate flaps. So I'll go to the computer for this. And start Xfoil. Oh, I have to go to my downloads. Okay, I'm just going to use an NACA airfoil for this for illustration, but this is all going to work even for any other airfoil. So I'll use NACA 2412. And just the way I normally do is I distribute 200 panels. So I've got 200 panels on this. Wait. No, I didn't do it properly. PPAR N200. Yeah, now it's become 200. Now, there's a menu called GDES. GDES. Oops. GDES. This is a geometry design routine. So you can make geometry changes with this. The thing that we use it most for is flap, trailing edge flap. So if you go to GDES, there's a sub menu. So you can put a question mark and it will say, these are all the things you can do with it. You can rotate the airfoil, you can translate it, you can scale it and do all those things. You can change the trailing edge gap if you ever want to do it, or change the leading edge radius. We normally don't do all this in the course because we do airfoil design using an inverse design method that's different from Xfoil, right? You can change camber thickness, which you will do in homework 3. But the one I'm going to talk about now is flap, right? Deflect a trailing edge flap. So let's see how to do that. FLAP. Now it will say enter the flap hinge X location. I'm going to use a 20% chord flap. So normally when people say 20% chord flap, that's the chord fraction of the chord of the flap. It doesn't mean the flap is hinged at 20%. The flap size is 20% of the full airfoil. So 20% chord flap will have a hinge usually at 80% or 0.8. So flap hinge location is at 0.8. And you can hinge a flap anywhere like upper surface or lower surface or in the middle of the airfoil. Those get into details. In our course, let's hinge the flap always from the middle of the airfoil at that hinge location. So for convenience, Xfoil gives you all this information right away. It says top surface is at Y of 0.03, bottom surface is Y of minus 0.015 at this X location, at the X location of 0.8. So if you want to put the hinge at 50% of the airfoil thickness at 0.8, then you have to put a Y that's in between these two values, in between 0.03 and minus 0.15. I mean, not a big deal, right? You can take the average of this and that'll be the Y. But after, if you can avoid doing that calculation, it's always nice. So instead, you can put Y over T. So Xfoil defines Y over T as 0 at the bottom and 1 at the top at that X location, right? So what we want is Y over T of 0.5. So if you want to specify Y over T, you say 999. That's just a code that Xfoil will understand as, oh, this guy wants to put Y over T and not Y, right? So now it will say, okay, enter flap hinge relative Y over T location, and you say 0.5. And enter the deflection. I'm going to put 10 degrees, plus means down, so 10 degree flap. And if you do that, you go here, and there's the flap, there's the hinge, the magenta line is the flap. And so this is called the Xfoil has some sort of nomenclature, and it calls, I think it calls this the current airfoil and this the buffer airfoil or something like that. Let's scroll up. Yeah, so this is, right now it has not made the airfoil to this geometry. This is still the airfoil geometry, and it's telling you this is what is in the buffer. If you like it, you can say make that the airfoil, right? And so you have to do that. That's an important step. So there's a command in this called exec, EXEC. That will set the buffer airfoil to the current airfoil. Right now, if you exit this menu, there will be no change at all. It will still be the original airfoil you had. So if you want to use this as the airfoil, then you should say exec. This is a very important step. If you say exec, now it will say current airfoil node set from buffer airfoil, whatever, something. It does some calculations, and it adds some points to make this flap a nice smooth transition, and does some internal paneling and all that. Now, so this is now, and then you have to get out of GDES menu. Once you get out of this GDES menu, now the airfoil is with the flap, and you can say, for example, upper angle of attack of 0, and it'll have this with the flap, and you can see that this spike is due to a discrete change in slope because of the flap, and that's real. Even if you do a wind tunnel test with a flap, you will see this change in pressure distribution in this place. That's why at large flap angles, there is a big adverse pressure gradient here, and that's why sometimes flow will separate off the hinge. That's just something you can't do a whole lot about. Okay, so that's how you do a flap. So remember two things: use y over t of 0.5, for which you have to put 999, and you can actually automate all this too. You can scriptify, put this in that script file. And so once you have a script file for angle of attack or flap angle of 10 degrees, if you want to put flap angle of 5, you just have to go and change that and change the output file and run it, and it'll do it. So two things to remember: use y over t, for which you have to put 999, and then remember to put exec to say, okay, that's the airfoil I want, and then get out of the GDES menu, and then the airfoil will have the flap. Okay. So you use GDES, flap, use y over t equals 0.5. In this course, some other time you may want to use something else, but right now in this course we'll always use this. Okay, I think with this you should have everything you need for homework 2. Hopefully you've started already. I think we have done a lot of stuff with Xfoil, but these are the final details you need for homework 2. Any questions? Yes?
I just had a question. I don't know if it's been answered yet, but in pplot, when you, I think it's option 4 is to save the plot as the PostScript file. It just saves automatically as post.ps. Is there a way to change that, or do I have to include that in my batch file to just rename it afterwards?
Yeah, so I saw your post and I went and looked at pplot. I thought there used to be some option, but maybe I'm not remembering correctly. So it looks like there is no option to specify a file name. So just write a little batch file or MATLAB file to, every time you run pplot, go and change the plot.ps to something else that you can keep track of.
Yeah, it just seemed weird to me, like there has to be a way to do it. Like,
Yeah, I thought maybe Xfoil has that. Xfoil can also create
yeah.
PostScript files, and it'll also write to plot.ps by default. But there is, I think Xfoil you can set the file name to something else. Save plotting options, maybe PLOP. Okay, I don't know. Let's just quickly let's run some airfoil at 0 degree angle of attack, and then I think hard copy current plot. Hard will make a hard copy, and it will say writing file to plot.ps. Even here it automatically goes to plot.ps. Let's quit Xfoil and then start again. If there is already a plot.ps, what will it do? Let's put a different airfoil, 23012. Hopper alpha 2. Now if I do hard, it still writes to plot.ps. Somehow I thought there was an option to change the file name. Maybe I just don't remember. I think maybe it's in my batch file and I'm remembering it as something in Xfoil. So what will this plot.ps have? Will it, I think, will it have multiple? Oh, it's going to do all this Adobe thing. It just overwrites it? Okay. Well, yeah, so you have to have some way to change the file name once you write it, which can be in the batch file. Okay, yeah, good question. Anything else? Let's see what it does. Yeah, it's just overwritten. But I think within an Xfoil run, within the same run in Xfoil, if you plot multiple angles of attack and say hard copy, it will create a PostScript file with multiple pages. So let's say this was at angle of attack 2, right? So if you have angle of attack in the same run, if you do angle of attack 4 and then say hard, and then angle of attack 6 and say hard, you'll have 3 pages, one for 2, one for 4, one for 6. I'm pretty sure that's how it works. So
you don't actually have to open pplot separately. You can do all the plotting in Xfoil.
You can. I've never done that. When I started using Xfoil didn't have features to do polar plot. You'd always do outside, and so that's the way I'm doing it. So I've not completely gone and experimented with the plotting polars within Xfoil. And normally, except rarely, I don't run Xfoil manually. I always put a batch file. I string together a whole bunch of runs and then I come back later and look at the results. It's just too tedious, and it's not usually worth it to keep running Xfoil by hand. So, okay, good. Any questions? Any other questions? Okay, let's go to the new topic, which is inverse design. So this is going to be chapter 4. So I'm skipping chapter 3, and I'll come back to chapter 3 later in the course. Okay, so what exactly is inverse airfoil design? So in the context of airfoils, it's the approach in which we prescribe the desired aerodynamics So normal way of thinking is what is called direct design procedure. The opposite is this procedure, which is inverse design. So in a direct procedure, you will give the geometry of an airfoil, then you'll go run X-foil or something and you'll say, okay, this is the performance. Now, this is not what I want. I want less drag here, more lift there, or something like that. Then you'll say, okay, how do I do that? You'll go and change the shape of the airfoil and then run it in X-foil and see how it is. Maybe it comes closer to what you want, maybe not. And then you keep on changing the airfoil geometry to see whether you get closer to the desired aerodynamic performance. That is often tedious, although there was a lot of progress in that. The opposite of this is direct. Here you specify geometry and keep altering So although this was, a lot has been understood with this, it's still a tedious thing. There's a lot of trial and error. So very early on in the 1950s or so, the inverse design started to gain some attention, even maybe 1940s. So there is a reason for it, and that's why I spent a lot of time in the beginning of the course talking about what is velocity distribution, what is pressure distribution, what is the importance of velocity distribution, how does velocity distribution change with angle of attack, and this and that. So often, so we are going to do the inverse design. And when we are saying here the desired aerodynamics, right? And that can mean so many things. It can mean a drag polar, or it can mean the aircraft performance or something like that. So that is like many steps into the design process. And if you try to do something like that, it can get very complicated, right? If you say, I want an airfoil for an aircraft that cruises at whatever, 300 knots, consumes only so much fuel, and then it stalls at something else. Give me the airfoil. That's like a lot of steps in between. If you can do that, then things will become too easy, and then there won't be need for too many aerospace engineers. But that's a very, very hard problem. A smaller step will be to say, I want this kind of velocity distribution. Give me the airfoil, right? That's a tractable problem, and that's kind of what we'll be doing here. So Sorry, I forgot to move this. Okay, so when we say desired aerodynamics, we are talking about inviscid velocity distribution. So why should we choose this as the desired aerodynamics? And the reason is there is a good connection between inviscid aerodynamics, inviscid velocity distribution, and the sort of performance parameters that we are interested in. So why inviscid? Because the area in the velocity distribution plot relates to lift and moment coefficients of the airfoil, right? We have seen this enough times so far in the course. And we also know that gradients, surface gradients of the inviscid so we know that the inviscid velocity distribution gradients control how the boundary layer develops along the surface, and therefore this affects the drag coefficient and CL max. Right, the boundary layer properties will control drag coefficient, and at high angles of attack, the angle of attack at which boundary layer starts separating and moving towards the leading edge, that controls CL max, stall. So the inviscid velocity distribution is a logical choice. So just as a quick example, let's take two velocity distributions for an airfoil. So let's say one velocity distribution is like this, and another velocity distribution is maybe like this. So if you know for a fact that these two have the same area inside, between the lower and upper surfaces, then you can say, just by looking at the inviscid velocity distribution, you can say these two airfoils have the same CL. And even if you don't know the area, just by looking at it, you can say that, well, looks like the area is the same, so they have pretty much the same CL. But what can you say about some other aerodynamic parameter? The pitching moments are very different, right?
Pressure gradients will be different.
Pressure gradients are different. So you know that this has got a sudden adverse pressure gradient. Chances are the boundary layer will separate here, something like that. But you can also say pitching moment is very different. So which airfoil will have more or less pitching moment? And when we say pitching moment, we're usually thinking of negative pitching moment. So which airfoil will have more negative pitching moment? The blue airfoil. So the blue velocity distribution will result in more negative CMC over 4. And you can also say the velocity, you can also say that this velocity well, I'll just say this red airfoil has got a rather sudden adverse gradient there, and it's going to do something to the boundary layer. Maybe it'll make it separate or something. It'll depend on the Reynolds number. It'll depend on so many things. And that kind of thing, you can run this airfoil in Xfoil and figure out what happens. So even though the inviscid velocity distribution doesn't give you the whole picture, it won't tell you drag, it won't tell you CL max, you normally, at least in the way we do in this course, and most of the time that's how things are done in airfoil design these days, you don't use the inverse design procedure in isolation. Anytime you get a candidate airfoil out of this, you run it in Xfoil, and then you develop a sort of feedback loop or something like that, like designer in the loop kind of feedback. So you run it in Xfoil and say, oh, this is, if I have this kind of adverse gradient, it separates the boundary layer, maybe that's bad, so I can go change the inviscid velocity distribution to be more gentle, that sort of thinking. So this is the reason why inviscid velocity distribution is a good sort of stepping stone to inverse design. You don't, ultimately you would like something even better. Like you would like to say, I want this airfoil to have this much drag and get the airfoil shape, but that's many steps down the line. And it's also usually not practical. For various reasons, airfoils are never designed for one condition. They have to work at many conditions. And even to know beforehand, this is the drag you want turns out it doesn't work too well. So in that sense, inverse design is a good, velocity distribution is a good input parameter for inverse design. So the inverse design method we'll be using is based on conformal mapping. So we won't go into this too much at this point. Towards the end of the course, we'll talk about Theodorson's method, which uses conformal mapping. We'll go into some amount of detail there, but just in very brief, using a very brief description. In chapter 3, which I'm skipping now, right? We'll do chapter 3 later. We'll talk about flow around various elementary shapes, and one of those flows is flow around a circular cylinder. So in conformal mapping, this kind of flow is known really well. We have the analytical solution for this. What happens is this flow is mapped using some complex variables and transformation to the flow around an airfoil. So there will be a transformation function. It's pretty mind-blowing how they came up with all this back in 1900s, or even before. So they figured out that they can transform the flow around a circular cylinder, for which the flow is completely known. You can calculate it easily, to the flow around an airfoil. So essentially the shape and the flow are morphed together to this shape. And in inverse design, what is done is, at least in the way we are going to do it, when you want a certain velocity distribution, the method will actually go and calculate the parameters of the transformation function, and then it will give the shape of the airfoil. So on Moodle, I've now put mfoil and profoil, I've made that visible. And there are some papers there that describe the theory behind the method we are going to use. So you can go read that and put it as optional reading. There's a lot of detail, and it's fairly complicated stuff. But go read it if you're interested, and you'll see that it's a pretty neat thing. So that's all I'm going to say about what is the theory behind it. We'll talk a little bit more about conformal mapping later on. But in terms of, there are a couple of varieties of inverse methods. So there are single point and multi-point methods. So single point method is where the desired aerodynamics which is usually inviscid velocity distribution, this is prescribed at a single condition. So usually you'll say at a lift coefficient of something, 0.5, I want this velocity distribution. And when you do that, the method determines method will determine the airfoil shape and performance. So airfoils are rarely designed to operate at one lift coefficient. They have to operate at several conditions. So performance at other CL values is obtained after the design process. On the other hand, I'll probably take just about half a minute. Let's finish this. On the other hand, if you have a multi-point method, on different portions of the airfoil, the desired aerodynamics is specified at different conditions. So for example, you might design the upper surface for a high alpha condition, and you might design the lower surface for a low angle of attack condition. And that's what, so we are going to use a multi-point design method. So when we continue in the next class, we'll talk about why this is actually so much beneficial, why that's really a cool thing to do. Okay, so I'll stop here today.